Hello, welcome to another episode of Car Chats with Herbie, and tonight I thought I'd discuss about how do we create a strong engine. How do you create structural strength and rigidity within an engine? Now, it can come down to the materials. We have methods such as casting, where a smelted or melted down metal is poured into a cast and left to set. Now, this is usually the weakest form of creating and forming an engine. And we have forging, where we have a metal which is in a unshaped form, superheated and then pressed into shape, and now that creates a different grain structure to the casting structure, standard cast. And we also have billet, which is billet is where a block of metal, the substance, is taken in a state, unformed state, and machined, usually CNC machined, and drilled and finely ground into a shape, so they can take the minimal amount of material away, leaving a lot of structural strength there, a lot of thick metal for the strength of the engine. Now, all these different forms have different grain structures. So if we go to a cast block, and you look under a microscope, you have a very uneven spaced of grain structures. So these metal particles are uneven and unpredictably placed, and it's not very formalized or formulaic in structure. You could sort of think of it like a tree. If you look at the rings of a tree, it's not tied together, it's spaced out and things like that. And this leaves little passages for cracks to form on the face of these materials, and also leaves the risk of torsional fracture from shear force. Now, shear force is force which opposes each other, like two magnets which you've got the wrong poles meeting each other, north and north, things like that, things that don't attract. Now, shear forces are usually shattering forces, high compression forces, so we don't want to be using a cast engine block with the application of performance, high boost pressures from turbos, high compression engines like diesels. Diesels are usually forged. Now, the structural strength can also be changed by how engines are formed. Are they formed from one piece? Are they all in one? Or are they put together through different pieces, such as a V-angled engine mated together? Now, that will be more subsequently, rocking forces will try to pull the mating surface, which is the weakest link. It will try to pull the block apart. Now, forging is probably your best bet, really, for cost and strength at the same time. Now, a lot of strong engines are based around forged engine blocks. Now, we've got a bit of traffic down here tonight. Forging, as I said, it comes from unshaped piece. It's highly heated, pressed, molded into shape with high pressure presses, things like that, with connecting rods, crankshafts, engine blocks. Now, the forging leaves a tighter grain structure, and there's a higher carbon content in forged metals. So the numbers, if you're looking at buying different metals, they usually start with, let's say a 5 140. So the 5 is the 5 or 5 140. The first two numbers or first letters designate the amount of alloy present in the steel and the metal. Alloy being quite a soft metal, quite a soft steel, things like that. That's the first part. The last numbers, the important one for strength, is the carbon content. Now, the higher the content of this means the stronger grain structure. Now, grain structure is, the molecular particle makeup of the metal. How tight is the grain structure? What different metals are within there? Is the graphite in there, which creates like what's called a grey iron, which is more resistant to frictional wear and has better torsional rigidity? Is the titanium, is the chromium in there? Is the nickel, is the copper in there? all these different things change the composite and the malleability of an engine block and its lifespan. Now, one of the strongest is billeting. Now, we take a solid block, we machine it into shape and create the desired parameters for, you know, the componentries to fit, usually very tight tolerances and things like that. It's reserved for one-off engine builds, and motorsport and things like that. Now, there is weaknesses within billeting, like there is 10 to 15% weaker connecting rod caps where the top of the connecting rod is, where the arch shape of the connecting rod is where it you know, where it mates over the crank journal, and then the cap's place. It's about 10 to 15% weaker structurally there than a forged connecting rod. Now, we've gone over, you know, the basics of sort of the types of engine blocks we have. Now, there's other methods of strengthening them. We can have reinforcement ridges within it. Now, you imagine this like a house with reinforcement beams. There's ridges and channels of metal across an engine, upwards of the side of the engine, usually built within oil ports as well, but they're like thick ribs. They're like a human's ribs. They're like thick parts of metal which can transition the force across and spread the shear force and the torque and torsional forces, vibrational forces across the block, leading to more resistance, especially if we're going into primary, secondary rocking motion forces, anything like that which can affect the life of an engine. Now, for example, the 2JZ Toyota Super engine has it's a forged engine, so it has a pretty tight grain structure of the engine block, and it has reinforcement ridges compared to its predecessor, the 7M GT, which was prone to head gasket issues as well. And unlike, they're both straight sixes of 3 litres, but the 2JZ has ridges and the oil passages are further away from the cylinder walls, which means there's more thick metal, meaning there's less likely for a fissure or crack to form across the plane of the engine block, or the cylinder deck, as you could call it. Now, those ridges, as I said, spread the forces across and things like that. A lot of engines use mixed alloys, mixed metals. So let's say you have, like some of the BMW engines, at the time they were overbuilt. They're using forged crankshafts in the early 60s, and they were using forged pistons, things like that. Mercedes were a bit strange. The OM engines, the diesel engines, which I don't know the German word, but what it translates to is, Germans are quite literal with translation, is oil motor. Now, that had forged, had a grey cast iron block, and it had forged rods and things like that. So it was pretty heavy built, but then it had a alloy based cylinder, which is a bit strange. But I suppose because it had a large capacity, they could double the thickness of the alloy, which you can do if you're using an aluminium engine block, cylinder head, pistons, all of this. Aluminium can't take the amount of pressure. Now, the average pressure a forged engine block can take is around 160,000 to around 200,000 psi of pressure. Now, I think that's like 18 tons plus of force upon a given cylinder, so it's a lot of bloody force. Alloy can only take around 60 to 90,000. So what they do, because alloy is 2 to 3 times as light as a steel, now what they do is they double the thickness of the moving parts, the reciprocal parts. By the way, an engine starts off with rotational movement and then it goes to reciprocal movement, which means it reciprocates, it basically repeats the linear motion over and over again, like you swinging a ball. It just repeat, so it's in time. These go back to early weather clocks and things like that, with rotating ball, which were weighted balls, which would reciprocate and be in time and repeat constantly. I think it goes back to like the 1700s, does all that. Now we've got some of the basics there. Now alloy engines have they're very thermally dynamic in a way. They expand and contract the metals such that there's a requirement for things like steel cylinder liners within an alloy engine. So there's a hardened mating surface, because if it's alloy and alloy, you would have too much expansion, the potential for the piston rings to mate and basically weld themselves to the surface, create too much friction, and their heat, there it would heat seize in that scenario the engine. So you need a mating surface which is harder, and also means you don't have to replace the engine block, which is very expensive, and you can just replace cylinder liners. Now, fun fact about those Ford Focuses in front, those Mark 3, I think Mark 3 Focuses, door sills, apparently they're rubbers in them, are quite crap. It's very unusual to see one without a flappy door seal coming out of them, out of the mouldings. Anyway, that's a bit of a random fact that you don't need to know. Now, strange engines that can take a lot of power, which are a little bit more unconventional than you would think. Let's say we've got the Super. It's a closed deck engine block, so coolant and oil port passages are further away from the cylinder and cylinder bore, meaning there's more space and thick metal on the cylinder deck, and this means there's more separation. It can take more heat, take more compression forces. The head gasket space is different, things like that. What this an engine like the N54 BMW, which is known as one of the modern 2JZ engines, is actually an open deck cylinder head, which is different in design. Inherently should be weaker, but for some reason it's very, very strong, and can take a lot of pressure and boost, and can take a lot of shear forces from increasing compression and things like that. And an open deck cylinder head is where you usually have liners placed in, things like that, within a block, and they mean that there's only a thin amount of metal between where the combustion processes are happening and then your coolant passages and ports here, and you've got less space for instances where there could be knock pre-ignition and things like that, which can have small pockets of combustion in the wrong areas at the wrong time, creating uneven pressures within the cylinder itself, uneven formations of compressive explosions, and this causes fractures within metals, cracks, and potential failure of cylinder wall, things like that. You can strengthen things like having liners like in alloy engines as well, because they have to have a different mating surface. You can't really have alloy and alloy, it would wear too quickly. It's a lot softer metal. You have things like chromium plated cylinder bores. You also have I think it's electrical charged or elastic, I can't remember the word for it. There's some fancy word for it, elastomer plated or something. So they use like a laser highly heated to heat treat it, so the metal structure, molecular makeup changes and is more resistant to heat. So it's basically heat treating the wearing surfaces. Now these are all methods of strengthening engines and things like that. So now you know how